Hello. Hello, everybody. It always takes a sec for that to show up. What? What is it, Umbra? My screen is black? It always takes a sec for it to load in. I don't know why. My OBS doesn't like me. That always happens. That literally always happens. What is that? OChem. Not OChem, thank God. Okay, statistics midterm. Okay. Hello. Hello, everybody. It's been a bit. Sorry, I keep meaning to stream and then, like, stuff comes up. Like, I had to go pick something up, like, on Tuesday when I was planning to stream. And then I couldn't stream because I was picking something up. Kind of how that works. Let me turn this down. Vaping ad on Damie's stream? Oh no. Like, anti-vaping ad? This music sounds appropriate for the vaping ad. I'm hoping it's anti-vaping. Where am I going? Measurement and data analysis. I haven't done any homework for this class yet. Okay, the one where the vape is like a therapist and it's like dye. I do not know what you're talking about. But, okay, wait, I want to do the extra practice. Where is that? He was like, you should do the extra practices. Extra problems. Here we go. We're going to start with these. Oh. Perfect. 16 pages. Oh, God. Okay, well, we'll just go through and we'll do some, and then because my midterm is on this Wednesday, so I have a little bit of time. I'm being a smart cat boy. I'm preparing beforehand. It's not like it's tomorrow. All right. Let's see. Okay, this music is like way too intense for stats. Where's my music? What am I gonna do? Not this. We're gonna do something else. We're not gonna listen to that. Listen to this one. Okay. Also, I have a print running in the background, so if you can hear, I have many fans in my room right now. Okay. True or false? A measurement with high precision has high accuracy. False. They are not correlated. It don't matter. Wait, why is my... Okay, whatever. My pen is kind of fucked up. I have it just set to one monitor, but it's on two monitors. Uncertainty is merely an estimate of the error in a measurement. True. That's what uncertainty is. Determining the weight of an object, Newton's law, F equals ma, where A equals g, is invoked. True, I believe. Precision error is also called random or statistical error. Okay, so precision error is like, precision is like repeatability. So yes, that is true. Okay, yeah, that's true. 1 pound mass is equal to 1 pound force on Earth. True, on Earth is the part that you need to, I think. Okay, you weigh yourself one morning with your clothes on. The fact you're wearing clothes introduces an error. This error is called bias error. because we're adding a known, well, I mean, I guess it doesn't have to be known. There are two general categories, bias and precision, but three practical sources of error. Practical sources. Well, statistical is one of them. You have statistical. You have... Fuck. I don't know what the three are. What are the three? Two general categories of error. Also, let me switch my tablet settings real quick, because it's gonna look... Oh, my tablet driver is not responding. That would do it. It says I need to turn off my computer, which I don't really want to do. Okay, we're just gonna write really big then. Three practical sources. Practical sources. What? Where does error come from? Okay, let me think. Practical sources. Fuck, I don't remember that. I need to get my notebook. Oh no. This is why we review. This is why we review, gamers. Oh, fuck, that's like my scary notebook. Oh, here we go. Practical sources. I remember writing them down. I don't remember what they are. It was like... Yeah, three sources of uncertainty. Wait, what are they? Wait, what? What are they? Wait. Huh? What are they? Wait, I wrote down three sources of uncertainty and I didn't say what they were. Well, what are they? Hello? Oh, here we go. Okay, well, three sources of uncertainty. Well, I guess uncertainty is just you are uncertain about them. Uncertainty is just an estimate of error, so I guess that's kind of, like, correct. So, statistical is one of them. The other one is calibration. And the other one is resolution? Yeah, resolution. So resolution is like the step of the device, so we can have error if like we're trying to measure 0.0032. If we measured a 0.003, because we can't measure a 2, that's resolution error. Calibration error is like our bias error, essentially. And this is like precision. Okay, wait, this is so scuffed. Well, this is also precision, statistical error. These two are precision, pretty much, and this is bias. Pretty much. Okay. Under what conditions would be using 9.80665 be appropriate? Always. No. Incorrect. Never because gravity is not acceleration. What? I think only at a location where it's known this precisely, because we were talking about it and like because gravity fluctuates like depending on how high up you are and stuff, obviously, but also just fluctuates depending on like where you are on Earth, and all that. So I think that would be right. Let's see. Ooh. Wait, let me not put his name. Did I already put his name? No, I didn't put his name. Good. I thought I just like put my professor's name up there. Hydrate. Thank you. Thank you, Mace. Wait, what did I do? I don't have water. That's all I'm here to do. Bye, Damie. Thank you. I have to go get water. God damn it. Fuck you. Okay, fine, I'll go get water. Give me 1 second. I've acquired water. Okay. Let's see. Alright. Conversions. My least favorite part of anything, but it's okay, it's important. Okay, the Reynolds number Re is a dimensionless number used in fluid mechanics and is defined as fluid density times fluid velocity. D is the length, and is the fluid absolute viscosity. Calculate the... Okay, so we want to do rho times, we'll do 1.16 kilograms per meters cubed times 0.30 kilometers per hour times 0.254 meters times 1.85 times 10 to the 5th Newton seconds per meters squared. Okay. Oh wait, sorry, flip these. Meters squared up here, and then Newton seconds. Alright, so we're gonna have to calculate a lot of things, but the things I do need to memorize are 1 Newton equals 1 kg meter per second, right, because F equals ma. Wait, what is an accelerator? F equals ma. Yeah, meters per second squared. Second squared. The other thing I need to know is pound force. So 1 pound force equals 1 slug foot per second squared. Yep, so mass length over second squared. And then 1 pound mass equals, right, 32 point something. 1 pound force. Wait. Yes, 1 pound force equals 32.174 pound mass feet per second squared. So those are the 3 things that I need to memorize, and that's all. I have to take stats one day for my degree. Pray for me, Damie. I'm not strong enough for whatever you're doing here. It's okay. This is not stats. This is just like more engineering stuff. Because like normally when you do stats, like this is not really the stats problems. This is more of like the data, the measurement stuff that we're talking about right now. Yeah. So this is like you don't actually have to know like this stuff for stats. This is not stats. This is just measurements. What the fuck, slug? Yeah, a slug. It's because like you know how like we measure everything in pounds in America, right? Like, well, pound is like a weight, so it's not a mass. So somebody came up with a thing that basically said like, what would the American kilogram be? And somebody decided that was called a slug. So we are left with slug. Okay, so I need to change what kind of stuff? Okay, let me change this Newton. So the Newton on the bottom, I'm going to say times seconds, and this one will be times a Newton. So a Newton on the bottom means that we're going to have seconds squared per kg meter. So this will cancel, and this will cancel, and this will cancel, and this will cancel. So we're just going to do some cancellation stuff right now. So the kilogram over here will cancel, the kilogram over here will cancel. And this one, so this number is like good. No need to change. This one is also good. This one will cancel here, and we'll do that one. So I do need to change this to m per s. So So 0.30 kilometers per hour times 1 hour over 60 seconds times 1,000 meters over 1 km. So in my calculator, oh shit, I have to get like a different, I don't think it'll be an issue if I only have my 4-function calculator for this exam, but he doesn't let us use a graphing calculator. He asks us to have a lower TI series, and I haven't bought the lower TI series yet because that's what you use for your engineering. Okay, it's just 5. So 5 meters per second. You use it for like your engineering examination or whatever, or your engineering, what is it called? Like license, essentially, I guess. Okay, so 1.16 kilograms per meters cubed times 5 meters per second times 0.24 for 1 meters times 1.85 times 10 to the 5th meters cubed over seconds. I'm just gonna say not meters cubed, it's just seconds, I think, because the meters cancel out. Oh no, kg doesn't cancel out. Wait, then where are my seconds going? And so meters squared. Oh, this goes up here. This is seconds squared. Wait, okay. This is the number. I can't believe it's just literally just numbers. But he wants us to be very specific about how we write things and writing everything out, so I'm trying to like make sure. Okay. Anyway, this over 1. I'm just gonna do all the units over here. So if we're flipping it, right, so it'll be meters squared. I lied, I'm gonna put the Newton over there. Over newtons times seconds. But we have a Newton over here, and a Newton is seconds squared over meters. kg. Meters. So one of these goes away. The seconds stay up top, so that'll cancel out there. This goes away. Yeah. There's a meter up here. Everything is very long. I wish my tablet drivers were working. They're not working, so kg goes away, meters go away, seconds go away. Cool, kg. Okay, so now it's a lot of work to just multiply 4 numbers, but that's okay. That's what engineering is about, right? Now I do have to check significant figures, so we're gonna do that in a sec. Okay, so we take the lowest number of significant figures. In this case, our 0.30 is going to have 2 sig figs, and so that would be, I guess, 5.0 meters per second instead. Yeah, because our initial dimension is that. And then, in this case, this is also 5.0, so our lowest sig figs, because we use sig figs for multiplication, but not addition, is going to be 2. So we're going to have 20, okay, wait, so, let me just write it, 2, 7, 2, 5, 4, 2, and then so we 1, 2, 3, 4, 5, so, 2.7, what the fuck is happening, times 10 to the 5th. Why is it going gray? I don't know. Strange. I mean, yeah, unless these are all yeah, they're not unitless, so. Okay, cool, that was A. Let's see. So for B, convert the properties listed in part A to English units. Pound mass per feet cubed, feet per second, feet, and pound feet second, feet per second. Okay. I think I can do that. I don't know if he's gonna give us like some conversions for, because like, you know, 1 inch is 2.54 cm. I think we should be able to do that though. Okay, so rho is equal to 1.16 kilograms. Oh, I don't know how many grams are in. Let's start with meters. Okay, so a meter is, so if we have 1 meter over 100 centimeters, and we're gonna cube that. A kilogram, we just, 1 kilogram is equal to 1,000 grams. I do not know the conversion between grams and... Oh wait, I keep forgetting I don't have my actual BTS thing up, but... Wait, is that not... Did I not set that up on this? Did I check this before and also realize that I didn't have this set up on this? Wait, it's not that. It's like a toggle. It's not that. It's not that. It's this. Hotkey. I straight up do not have it on this. Okay, that's fun. Can set it up right now. Let's see. Where is it? This one. And then, how do I do this? I like have to save a scene. Yes. Yes. And then a hotkey. Fuck. So professional. Hotkey action. Change scene. Toggle item scene. Cancel. I thought I could like turn it on for like a... Yes, stop after 10 seconds. There we go. So now if I can do that. Did it work? Nope. Let me see if I can... Oh, it just doesn't work. I love that. Oh, I didn't click the item scene. There we go. There we go. Yes, no, maybe? Does it fade? Yeah! Okay, we win, we win, we win. We stay winning. I don't know how to convert grams to slugs. Wait, so it's pound... They're asking for pound mass. Not slugs. How the fuck do I... What is a pound mass in grams? What is the... How to convert kg to pound mass? Like, I don't know what's the formula. Is it like... Nope, that's wrong. I don't actually know if he ever showed us that. What can you conclude about the dimensionless Reynolds number dependence on unit system? Let's see. Well, I guess it kind of depends on the sig figs. I don't know if he would give it I don't know if he would give us this or not. Because he literally said that we only have to remember, like, the 3 things where it's like, okay, you have to remember 32.175. 174. But everything else should... Okay, I'm gonna skip this, because I don't want to do more units. Let's do actual stats. Okay, here we go, here we go, here we go. Actual stats. Alright. Swag. Okay. The sum of all frequencies in a frequency distribution equals 1. Yes, true. Relative frequency is the same as probability. Relative frequency is the same as probability. I think that is also true. Let me see. I think I remember this. He didn't actually lecture on this in class. We had to watch a video, but... Let's see, where's my relative frequency? Yep, probability. Because you're saying, like, it's out of n, or whatever. What statement about third quartile is true? The third quartile is the range of values below the 75th percentile. The third quartile is the range of values above the 75th percentile. Third quartile is the range of values between the 50th and 70th. It is the value such that 75%. Yeah, the quartile is literally just a percentile, if I remember correctly. It's just a specific percentile. Like, the third quartile is the 75th percentile, and the percentile is just like, you know, if it's the 74th percentile, it's a number, essentially. I think it's a positional thing. Where's my quartile? Yep, 75th percentile. Cool. 16 measurements of temperature range from 66.5 to 81.8 degrees Fahrenheit. Select the most appropriate bin assignment for this data. Okay, so bin assignment, we want to calculate first, we want to calculate the number of bins we have. It's 16, so that's a lot smaller than 500 or whatever is it 100, 500? So the thing we want to use is the weird one that looks hard. I know, that's such a great... Let me pull out my equation sheet. Oh wait, I should look at the equation sheet. Maybe he has the... Where is the equation sheet for midterm 1? Exam 1, there we go. Ah, okay. So it looks like he's probably not going to give us the... Anyway, so we're going to use 1.87 times n minus 1. 1.87 times, so 15. Or I'll do 16 minus 1 to the 0.40 plus 1. So that's what we want to do. So do 15 to the 0.40. This number times 1.87, and this plus 1. Now I forgore k. How do we use k? It's like k divided by n, right? Wait, k is the number of bins that we have? No. That's like the bin width, I think. I think we round down, so I think our bin width... Where's that number of bins? No, I think that's number of bins. So then we do 81.8 minus 66.5, and this divided by this. And that gives us our bin width, 0.2. Uh-oh. I forgot. Wait, let me look at my histogram discussion. Let's see. Splits data. Okay. Bin width. Yes. Okay, no, so I did it right. K is the number of bins we have. So, okay, I can't have K be like a shitty number. If K is 6.5, I guess we should have 7 bins then. I don't know if he said round up or down. Let's see. Do you round K up or down? Do you round bin number up or down? Stats. This is the number of bins. Round it up. Okay, cool. That's just what Google told me, so maybe it's wrong. But, okay, we want to round it up. So 7 bins, so 15.3 divided by 7 is like 0.2. It's still like 0.2, and none of the answers here are 0.2, right? So like, you start at 60... Well, okay, wait. Maybe it's talking about the number of bins we're choosing, rather than the bin width, because the number of bins we want to have are... 7. 7 bins. So 1, 2, 3, 4, 5, 6, 7, 8. That's 8 bins. Wait, what? None of these line up with this thing. It's 16, so you have to use this. And then... Because I feel like 0.5 is way too big, right? This one is way too many, though. 1, 2, 3, 4, 5, 6, 7, 8. Wait, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. They're both 8. Hydrate? I do have water on me. Well, not on me, like, near me. Thank you. Thank you for the hydrate. Sorry, I was checking my 3D printer. These bins suck. I guess the most accurate bin... Well, okay. In my brain, B sucks ass. Nobody knows what 8.45 is. 0.845. Oh, you. On you. I have water inside me as well. I'm gonna go with A. Because it's the smallest... I guess kind of closest to 2. Doused. It's not close to 2 at all, which is, great. I love that so much. Ooh, okay. This is a good one. Box plot. Everybody's favorite. That was a lie. I'm actually, I don't know, I like box plots better. Okay. So this is our min value. This is our max value over here. This is our mean. No, that's our median. Lol, 50th percentile. This is our 25, and this is our 75. Men value. Our men. I wish it was men. Okay, the mean. We don't know anything about the mean. But, I mean, I guess we can say that... Oh, wait. This is, like, the middle of the box plot. That's probably the mean. I don't know. Maybe... I'm gonna say the mean is less than, because that's all I can say. It is not likely the population is Gaussian, because, this thing is way off to the fucking side. That's crazy. Population is unimodal. I don't know. The population is symmetric? I don't think so. Not likely. Because it's... I mean, the median is way over. Like, it's kind of like this. You can tell the mean in relation to the median based on the skew of the plot, right? So, like, the middle of the box, right? Because the whiskers, basically, my professors, if it's skewed right, you have mean... greater than median. Wait, why would you have... Wait, let me think about that. The median value is like... Is the one at 50%. Oh no, yeah, that would make sense. That would make sense. That would make sense. Because, like, you have more numbers, like, that are high. And if your median is, like... at 50%, like, you're gonna have a shit ton of stuff over here. Is that what you're saying? Is non-resistant to huge values, so it's pulled towards the skew. That's a lot of... Okay, wait, the population is unimodal? I don't know if you can say that. We can't tell that from a box plot, right? I don't think so. Because, like, it could be, like, doing this or something. It could be doing that. I mean, it probably isn't, but, like, it could be like that. Who knows? I don't even know if I have answers to these questions. I'm just doing them, so I don't know if it's gonna help. Oh, okay, let's see. Okay. A statistical tendency that we did not discuss in this course is the mid-range, defined as x max plus x min divided by 2. Why is that not as good as measure of central tendency as the median is? Because outliers. That's all I need to say, I think. Like, if you have, like, if most of your data is, like, in here, right? Like, okay, And like our median is like right here. And then you have like one dude all the way out here and one dude all the way out here. Or not even that. If you have one dude here and one dude all the way out here, your mid-range would be like there, right? But like that's nowhere near most of your data. That's what I'm gonna say. That's my great explanation of science. Median. Mid-range. I think that's right. That sounds about right. Ooh, okay. For a particular Gaussian variable having the following box plot, answer the following true or false. This is good. We like Gaussian things because we can do shit with them. Otherwise, you can't really do anything yet because we haven't learned about about S's. We've only done sigmas. Okay. The mean and the median are the same value. True. That's in the middle. That's our Gauss. The range of just the box portion of the box plot is greater than plus or minus 1 standard deviation from the mean. You've only done sigmas? Oh, wow, Damie flex. Bad gesture, fire him from the cannon. No, that was good. This is 50% if the data is contained within the box plot. And our Z is like 63 or something. So the range of is greater than. No, it's false. I think it's like 63 or something. I don't know. I could look at a Z table. I don't need to do that though. The number of measurements between the first and third quartile are equal to the number outside the box portion of the box plot. The number of measurements between the first and third quartile. Okay. First, second, third. Between these are equal to the number outside the box plot. True. The fact that the box is between the whiskers indicates this. Nope. False. That's a false. Well, it's a Gaussian. It's a Gaussian. Okay, I feel like this is kind of misleading, because if you said for a particular Gaussian variable, you're going to have a unimodal distribution. There's no Gaussian distribution that's not unimodal. So, like, the fact the box is between the whiskers indicates the distribution is unimodal. Sure, anything can indicate it, because we know it's Gaussian, but, like, the box between the whiskers doesn't mean that it's unimodal. Right? Like, I'm gonna say Gauss is always unimodal. Omega lol. If you ever have me as a student, I will write omega lol on things. I'm sorry about that in advance. Actually, you know what? No, I'm not sorry. It's fun. Okay. Ooh. This is a 4-point question, I see. This is not actually that bad. I was a little bit worried. There's some things that I want to go over, but like I wish I could like check my answers, because I feel like I have a pretty decent understanding. But okay. The meter to the right is accurate to the 4th decimal place. Is accurate to the 4th. In a sentence or two, assess the correctness of this statement. Okay. This is the meter. Let me move my big fat head out of the way for a second so you guys can see it. Okay. I am assuming the distinction here is based off of the outer ring, which is giving us only like those little those little check marks, right? So our resolution of outer ring equals basically just 1 divided by 2 equals 0.5, right? So plus or minus. So I'm gonna say, like, just based on, because I have no idea. I mean, right, like, if you see a meter like this, it could be doing some stuff behind the scenes to, like, actually accurately figure this out, based off of, I don't know, like, maybe it has a meter that measures, like, RPM. Hello, some math? Yeah, it's statistics, it's kind of math. More data than the math part of stats, but I think this is the last one that I have before I'm just gonna do the more math stuff. But it's also not that hard. Like, it's not that hard math, but it is math. I'm gonna say, unless meter is not connected, I'm just writing badly because everything is switched out. Currently, I read my lesson on partial differential equation for my exam tomorrow. Oh, you have an exam tomorrow? Good luck, good luck. You got this, I believe you. Believe in you. Not connected to the outer ring. Which it could be, right? Like, I mean, who knows what's going on? It could be completely disconnected. This is why I dislike classes that are like, let's be specific about things, let's be particular, let's be detail-oriented, and then the question like this, and it just assumes that you make an assumption that the meter and the ring are connected. I finished top 5 on my algebra exam last week? Yo, congratulations! Oh my gosh. That's awesome. It cannot be accurate to that place, since the resolution uncertainty would be roughly plus or minus 0.5. I don't even know if this is in units. I'm just gonna say units. The exam was awful. The average was 11 out of 30. Oh, that was like my linear 1 class. But linear is not hard. It was just people were bad. Well, my teacher was not very good, unfortunately, but I did well in that class. Teehee. You had 15.5? Oh my gosh. What was it, like, really long? Or was the content just, like, really hard or something? Meaning it's nowhere near accurate to point oh what? 0.00005. Lol. Okay, let's do one where I don't have to write as much. Because writing is not going to be very easy. Ooh, okay, here we go. Saying giant text. Do not use slugs or kilograms in your analysis. Okay, King, okay. I should probably ask him if we're gonna get, like, The content was really hard. If you want one of the equations, finds a ring which is isomorph to z square root of 3 over 2. Do not use slugs. Don't. He's very specific. He's like, and I get it, because, like, in the real world, it would be really dumb if you just, like, mixed up your unit systems, like, as an engineer, like, if you were trying to, like, do analysis. But it's just really funny, because, like, he's like, guys, you can't use them. You can't use them. And I'm like, okay, I'm not gonna use them. Okay, I get it. Fine. Isomorph? I don't even know. I kind of want to take a topology class, but, like, I have a lot of classes to take. Ooh, okay, some probability. Finally. Okay. So this is relative frequency. Never mind. We're not actually doing calculations. This is just the probability. Okay, what is the probability of obtaining a measurement between 90 and 105? So this is the top of the box, I believe, is 90. I forget how Excel does it. Is it the top? God, I really hate that Excel does that because, like, it's actually kind of dumb of ass. Because you have to, like, remember that it's the top or the bottom. And in addition, the exam, it wrote a well-known ring, and the answer was x over x squared. I don't know. Is that well-known? Is that not well-known? I'm gonna guess it's not well-known. Excel uses the upper limit and puts it in the center of the bin, is what I wrote. So 90 is the upper limit. So 90 to 105. The upper limit of this bin is 105. So that's these. So we have to add 1.0 plus 25 plus 30. So 0.1 plus 0.25 plus 0.30 equals 0.65, so 65%. Well, it says what's the probability, so I mean like 65 out of 100, I guess. 65 out of 100. Doesn't really matter. For me, it's not well known. It's a ring of 4 elements. Oh. That's fascinating. I don't know what rings are. Like, what is a ring? What is a ring? They sound cool, though. They sound neat, actually. Okay, can you, like, explain it, like, not as, like, a definition, but, like, you know, as a, like, not the formal definition. Some way that I can understand it without knowing the formal definition, I guess. Or, like, a semi-formal definition. Okay, 3 measurements fell within the range of 110. So that's 3. So 5% equals 3 measurements. Are any measurements missing from this graph? And if so, how many? Well, I think that's kind of a red herring, because I think they just want us to add up all of them. So let's see. This is 0.5, 0.5, so that's 0.1, 0.05, 0.05. Then we have 0.1, we have 0.25, we have 0.3, and 0.15. So this is... Let me just put these all in my calculator. So 0.1, or so 0.2 plus 0.25 plus 0.3 plus 1.5. Oh, whoops. 0.15. Oh shit, are we actually missing some? Wait, I need to do that again. Let's see, this 25 and 15 is 40, 70, 80, 90. Oh, they are missing. Yes, we are. Yes, missing. Yes, missing. And they gave us 0.5, so it would be 6 measurements. 6. Wow, it's kind of crazy you can figure that out. 6! That's so many! Math and Pokemon would be like, do not use Slugma in your analysis. I wish it was Slugma. I wish we just had, like... I don't know what Slugma looks like, but this is what I remember Slugma looking like. I think I just drew Gary from SpongeBob. And then I think they had, like, a big drip. What does Slugma look like? Slugma. Okay, not like that at all. The big drip was correct, but everything else was wrong. This is what Slugma looks like. You versus the girl she tells you not to worry about. When I come home, you better not be Damie V2 versus Slugma. Oopsies. Oh boy. I like Slugma though. I like better than I'm killing him. Sorry, he's dead now. Okay. An object with velocity. Sorry, I just got really depressed. Okay. V equals 141 feet per second. And has a kinetic energy of 8.71 feet per pound's force on a planet whose gravity is 9.807 meters per second squared. What is its mass in pounds? Okay, we're looking for pound mass. We know 1 pound force equals 32.174 pound mass feet per second squared. My brain was buffering a little bit there. Okay, what is kinetic energy? What is energy again? Energy is in joules. Oh, why do I not remember? Wait, do I actually have to like... Oh, the equation for kinetic energy is K equals whatever. Thank God, I would have forgotten that. Okay, let's just do like... This is given. It is a set which have the same property of Z for the operation. Is it like a can you visualize what a ring is? Math ring. Visualization. Visualizing groups of rings. Basic ring theory. Whoa. Yeah, you can, but it's specific for each ring? That's cool. That's neat. Oh, my brain just broke. Let me solve for V. V equals 2KEM. I really shouldn't call it like that. I should call it like that, if anything. It should be K. I'm gonna call it K. Cool. It's gonna be, yeah. Wait, why did I solve for V? What the fuck? Why need to solve for M? Oh boy, it's one of those days. 2K over V squared. Okay, now we say substitute variables. Substitute variables. Variables. So M equals 2 times 1558 pound force feet, I think. Oh, feet pound force. That's kind of weird. I'm gonna put pound force feet. There's geometric algebra, which is geometric things, but with groups, ring, fields, etc. I also started statistics this year. It's awful. It's like a little awful, but like it's not that bad. Feet second. Feet, wait. I need to flip it, so 1 over 141 second over feet squared. Wait, but then I'm gonna end up with the pound force. 1 pound force. It says do not use slugs is the thing. Oh wait, no, I can just change it to this. Lol. 1558. Wait, did I skip a number? I dropped this at 0.71. Statistics is like, the statistics that I need to use is honestly, like, not that hard. I actually kind of like it. Like, this class is becoming more of, like, a class that I like, because at least they're so specific about things, but at least they, like, know what they want. Whereas, like, my other classes are really bad at communicating what specific things they want. in the statistics I study, you have some numbers and you try to find out the law of probability which follow these numbers, and you can describe the error, etc. Yeah, that's what we're doing too. It's just a little bit more focused on engineering. So like, for example, there's probably a problem in here. Let me see if I can grab one, I'll show you. Yeah, wait, where is it? Okay, this is a good one. This one. Like, this is later, we'll do this one later, but, so yeah, like, the library has a weight capacity of 2,500 pounds. You have like a mean weight of Americans and a standard deviation, and you need to determine like how many passengers can fit in that elevator without it overloading the load, essentially. It's kind of like I don't really know how to describe it. This is more just engineering, like the kind of stuff you would be doing in your reports. Like, let's say you're doing let's say you're doing like structural analysis on something like FEA, finite element analysis, and you're, you know, calculating strains and stresses or torsion or whatever, and you know, you need to write down all your equations and things that you do. This is more like you have to figure out how to write that properly. Our program here at this place I go to is pretty. It's pretty focused on like very applicable things. I do things like that. Oh, that's so cool. I like that. I like that kind of stat stuff. Like, I don't really like other stuff as much. I don't know. Like, the math stuff is kind of cool. Where does my other seconds cancel out with? Oh, a second squared. Lol. I'll cancels and that'll be in pound mass. Yeah. Some questions with some... No questions with some context is pure theory. Yeah, it's like more mathematical analysis type stuff, which makes sense because you're a math major. I love that. I am gonna probably try and take some math stuff, but let's see. 0.593. Oh, look at the theorem. Wait, I'll look at it in a second. Let me just check these sig figs. 2 is not gonna have any. That's gonna have way too many. Gravity, wait. Wait, where do I use gravity? Wait, I don't need gravity. Do I? I don't think I need gravity. Because I can convert pounds force to pounds mass. Oh! This, I think, only works if we have the gravity here. I'll ask him about that. Let me write down some of the questions I need to ask him about. He has office hours, but his office is kind of far from where I live, so I don't really want to have to go later. Wait, no, I'll write them down here. So I need 2 questions. For KE question, does the pound force, pound mass conversion only work on Earth? That's just like I'm pretty sure that's the point there. But yeah, so 0. Oh, and then I just have to check sig figs. These numbers are all very significant, apparently. Oh, 141. So 3. So 9,594 pound mass. Okay, let's see this theorem that you're talking about, because I'm interested. I honestly thought, like, I was a big statistics hater is the thing before before I took statistics, and because I thought it was like, let's see, the Kolmogorov-Smirnov statistic quantifies the distance between the empirical distribution function of the sample and the cumulative distribution function of the reference distribution. This is interesting. Wait, so this is like... But like, what do you... Oh, just error? Okay, I don't know if we're gonna do this, but like, we do have to do error approximation later. It's just gonna take us longer to get there, because we have to take some side quests first. We're kind of just doing Gaussian populations as well. Like, the two things that we do are, like, we pretty much only study infinite populations, and at least for now, we're just doing Gaussian stuff, because the measured quantities that we measure are sometimes Gaussian, sometimes not, but like, for right now, we're just doing Gaussian stuff. Yes, Gaussian law is most used? Hell yeah. My boy Gauss. We love him. Okay, let's see. Let's go back. Okay, we did that one. Ooh, the lead content in... Okay, we can do this. Oh, maybe I can't. Wait a second. Oh. Okay, no, we're chilling. We're chilling. They gave us some... I was a little worried. They said calculate the mean, and I was like, I'm gonna get rid of this. For now. Okay. Have I seen the x squared law? No. Maybe? Probably not. Oh, draw the box plot. Okay, okay, okay. Okay, so calculate the mean. Okay, so mu. Well, it's a sample. It's x bar equals x bar of how many do we have? 30? Equals 1. Wait. Oh, that's a standard deviation. Okay, okay, I should probably say, like, he probably wants us to say, like, model, and then, like, put our equation. We probably don't need to do that. He's probably gonna be like, why did you write that, you big dummy? But it's fine. X bar is 1 over n times the sum of x, right? So 1 over n, sum of x1, so we have plug in vowels. So 1 over 30 times 111.43. And when we do an average, we add an extra decimal place. So 111.43 divided by 30. So that's going to be 3 point equals x bar equals, I'll just put x bar of 30, 3.714. And then we'll do the other model, which is our S. So it's 1 over n minus 1 times sigma x1 minus x bar. Oh, okay, cool, they give us that. And then this whole thing, this squared and this, wait. They give us the sum of it squared? Yeah, they did. Sum of that squared, and then this to the 1/2. Root sum. Took xi variables which follow that. Sum of x... Whoa. Took xi variables which follow n through 1. S equals sum of x1 squared for I equals 1. I equals 0 to n. And then s follow the x squared law? I don't think I've seen that. So 1 over 29 times 46.87. And this to the 1/2 equals s of 30 equals... I don't know what it equals. Square root of this. What's our standard deviation? 1.2. For standard devs, we also add an extra decimal point, so 1.2 and 1. Oh, it's used with Gaussian vectors? I don't know what Gaussian vector is. What's that? Okay. Draw a box plot in the figure below. Show all calculations. Okay, so to draw a box plot, we need like 5 things. We have the mean, but we don't need that. We need the median. We need the max value and the min value. Okay, so we can get the max. Max equals what? 6 point, and min equals 0.89, and we need the core Q1. Now the way we find that is by looking at the equation sheet and percentile I over n plus 1. Okay, we need to solve for I. Okay, we'll just do it real quick. Q1. Right, so I over n plus 1 equals 0.5. So I equals 0.5 times n plus 1, which is going to be 0.5 times 31. Ooh. 15.5. What does that mean? I can't use that. Wait, 15.5 is not an I value. Hello? Wait. It's also not... Wait, am I getting this wrong? Am I donking this up? Let's try point... Well, it is 0.25 also. Let's... I over n plus... Wait, I equals 0.25 times n plus 1. I have 30 values. That's not gonna come out nicely, though. Do I round up? What is this? 7.75? What does that mean? Is that here? Took x, I, some random variables, x equals xi. X is a Gaussian vector if all combinations of xi follow a Gaussian law? Huh. That's interesting. Okay, find a percentile. N over n. Yeah, wait, what? This is like... But it's gonna give me a shitty thing. Okay, you round it, apparently. Do you round it? It looks like... You're gonna go study? Good luck. What the hell? Oh, number of values below x. Oh, I see. I see. So yeah, so it is 8 then. Okay, so 8. I'm gonna do 0.50 equals... Okay, 16. And then... $24? Is that... Okay, I don't know if that's right. Okay, I might be, like, super silly, but I'm gonna say, for percentiles, do you round up or down for I? First I, when solving for I. Okay, we're gonna say up all the time, because, I mean, that makes more sense, because it's, like, values below, but I don't know. So 8, 16, 24. RR 8, 16, 24. So then we just have to draw everything in. Okay, so 0 point, let's just put a 1 in here. With these tick marks. I don't need to write a 1 there. We know that if there's a tick mark here. 8, 9, that's like here. And then 6, 5, 3 is basically here. And then, what else have we got? We got 3.11, basically 3. We got 3.65 here. And then 4.71, so 471 is kind of like here. Let me draw that and that. Kind of. Appropriate bin width for a histogram. Okay, that's chillin'. We just used that K equation we did before. Yeah, so K, right, K equals 1.87 times 29. Oh, I want to ask if we round this one up or down as well. .191. I feel like you round that one for histograms. Round K always. Round K normally, or K. We'll just say 8. Wait, the bin width is 8? No. No, that's how many bins we have. Okay. Lol. So width equals our spread, so 0.89, 6, so 6 minus 0.89. This divided by 8. 6.53 minus 0.89 over 8. 0.705. So, I guess 0.7. I mean, yeah, I guess also rounding. Why is rounding like the hardest thing ever? Rounding W? Because, like, would you want to just round that to 0.5 and do it like, I don't know. Determine the labels and frequencies for the first 4 bins. Okay, so 0 to, I'm going to say 0.5. The label would be 0.5. And then you have 1, and then you have 2. Sorry, 1.5, and then you have 2. And frequencies? Okay, how many of the values fall in here? To 1? Just 1. Wait, none fall in 0.5. So 0.5 to 1. So that'll be what? 1? 1 out of 30. 1.5. 1 again? This seems maybe like a bad bin size. Maybe not, maybe not. So, 1.1 to 1.5, and 1.5 to 2, and then 2 to 2.5. Okay, so we need to do 1.5 to 2. Yeah, I did that one, sorry. 1, 2, 1, 2, and 2 to 2.5. Wait, were there 0? Wait, what am I doing? Wait, 89 is in there, yes. 1 to 1.5, 130, yes. 1.5 to 2. 0. Okay. Okay, I see how it is. Alright. That's pretty good. That's a good one to do. my print is almost done. Exciting. Doing 3-hour prints kind of sucks. It's more of a 4-hour print, so I'm not trying to make a habit out of that, but kind of a lot of my stuff I'm printing lately is big boys. Okay. Here we go. Oh, big multiple question. Oh, this one's great. This one's awesome. Oh, I really like it when we get into like the stats side of things and less of like just the device stuff. Okay. Choose the correct equation by letter that you would apply to the following scenarios. Okay, the boats on Disneyland is smaller relative hold 15 passengers each. Using the weight, what combined passenger weight? Okay, we're talking about combined passenger weight, so we care about... Oh shoot, wait, this is not the one that is talking about it. Let me grab my equation sheet here. We have a combined one. Wait, where's our combined equation? Oh shoot, which one do we... Wait. Using the parameters of the population. Well, so we are using parameters of the population, so it's not going to be x bar. Wait. Oh shoot. Wait, does he not give us n? Wait, where's our n equation? Oh shoot, he doesn't give us the... No, he does. Oh shit, how do we solve that? Oh, here it is. Mu equals 1 over n times x bar. Yeah, so then n times mu equals the sum of the... Sorry, the sum of the x's, not the sum of the x bars. I think we say we want... Okay. So parameters of population. So we're gonna get rid of... We're not trying to find a sample, right? So neither of these. We're trying to find mu equals x or x equals mu. I believe it would be x equals mu. That like kind of makes sense, right? Like we're trying to... I'm gonna say A. Oh, these are good questions. He might do something like this. Oh, okay, so the temperature in the room is measured. So we have a sample. The population is estimate the true temperature. That's gonna be D. I think. Wait, is that true? We are trying to... No, we want to do... I think we want to do C. Oh, boy. Wait, this is hard. Wait, okay, estimate the true... So the temperature in the room is measured 50 times in a particular location. So we have an X bar. We're trying to find the true temperature, which is just X. But we don't have the... We don't have the mean. I would say C and B, right? Oh no! Okay, wait, let me see. Heights of people have well-known parameters. Okay, population is known. You were designing a doorway. What range of heights comprise 99% of the population? That's gonna be A. Yeah, pretty sure that's A. You're attempting to measure the temperature of a water bath, but you're only using one thermocouple in a fixed location. The water temperature varies from location to location. In the previous test, you measured the variation of the temperature, found the standard deviation. Okay, how well does your single location estimate the mean temperature of the entire volume? Holy shit, okay. I feel like I should like write out more for these. Let's just try. I'm gonna go back to the other ones. I want to like write out the variables we're given. So we have an X. So we have a sample. We have the population population standard deviation, right? So that's like very much given, right? At many locations. And we're saying we have a sample, X, which means that we can have an X bar, I guess. We're looking for mu. So Cool, so that means we need C. Yeah, we're looking for... Cool. Okay, that makes this way I think is probably more reliable than what I was doing, just like thinking about it. Okay. 8 baby aspirin is an adult dose if the production of single baby aspirin tablets as an average. Okay, so production, we know that the mean is that and the standard deviation is that. What is the total dose you would expect? The total dose. So that's the sum. Wait, okay, total dose. No, we're looking for 8 times a single dose. So we're looking for x equals what, right? We're looking for like 8 times x equals what? So we can use A, right? Yeah. Okay, what would the standard deviation of a population be? Cool, so sigma equals what? Well, I'll put it down here. So that 85% of a population falls within 20 units from the population mean. So we know the population mean. Let's see. What would the standard deviation of a population have to be so that 83% of a population... This is more solving for Z. We know what... Essentially, we know what Z sigma is. Z sigma equals plus or minus 20. So we need to find Z, I guess. Z equals what? Which equation would you use? I mean, I don't know if it really matters, because we're not given actual population. But what would we use? Oh, from the population mean. Oh, okay, that would be B. Right, so it's plus 20 units from that. Wait, no. No, it's A. It's A. Fuck. This one is hard, but good. This one is good. I'm gonna ask him also, are there answers to these to check? He's probably gonna say there's not answers. Are there answers for the extra questions? Oh, fuck, that's hard. Okay. It takes 15 minutes to fill an airplane with jet fuel. The flow rate is recorded once every minute, and you can afterward calculate the mean. Okay, so we have the population mean, and we have the density. Knowing the density of the fuel, how much weight have you added to the plane? Wow, okay. Well, I feel like this is going to be a sum question, right? Because, like, we'll have to sum it up. I think we need a sum in there. Sum of x's, right? So if we're doing sum of x's, that means we need to use the mu equals stuff. So we'll need to have a mu. I think it's going to be B, right? Because you'll have like mu equals sum of x over n. So then you can like figure it out. I mean, you're going to have to, it's not going to be raw, right? You're like going to have to take the flow rate and turn it into how much stuff you have. Like, yeah, that makes sense. That one I think makes sense. Let me go back to the first ones real quick and see if we can do it. Okay, so hold 15 passengers using the weight parameters of the population. So we have mu and we have sigma. What combined passenger weight? Okay, we're going to be using B. The temperature in this room is measured 50 times in a particular location, so we have x bar. I mean, we also have S, but that doesn't really matter. We have the population standard deviation. Estimate the true temperature. Okay, so the true temperature is going to be X, but we want to estimate X, I guess, with the... Wouldn't you want to use, like, mu equals x bar plus You want to use C, maybe, and then use that to calculate X. Yeah. So this, and then A. I feel like that's not a great question, because I don't think you can just use that, but that's fine. Okay, they have well-known parameters, so mean, standard deviation. You're designing a doorway. What range of height? Oh, this is the same thing that's just like, it's Z. Which equation do you use? We don't have a sample, so, I mean, I guess you just kind of use, you're trying to, like, Z equals what? Or, I mean, I guess you're using A. Yeah. You just don't use D? What would I use D for? Let's see. If we have the mean, the population mean, which is, I mean, maybe we do, and you also have the population standard deviation, and you take a sample. Like, what? You could just calculate it from the sample, I guess, is my question. Because at least, like, if you're trying to find the population mean from, you know, a sample you took, with assuming that the standard deviation is the same as the populations, which it definitely isn't, but, you know, it's whatever. Because it's a class. Then you could do C, and B is like, okay, I have an X value, like I have some value, right, that I know from a set that I measured, and I know how much, like, the standard deviation is, and I want to figure out, like, within confidence, however many confidence, like, what the mean would be. And then the other one is like, okay, I know the mean, so, like, what confidence is X at? I just feel like D is, like, not useful at all. I think D is just there because he needed another equation. That's my that's my guess. I don't even know if he gave us D on our equation sheet. Let's see. I mean, I think he kind of did, because he's saying, like, you know, x bar equals mu plus z sigma over n, and mu equals, yeah. Yeah, I guess. And then S, and that, and then... Yeah, the only ones that are a little weird are, like... I don't know what the big N is. Oh, I guess the... Let me see how we did it, because we did do a problem where we added... Whoops, we added a bunch of stuff up. Just did, like, one, but that's fine. Confidence intervals, no thank you, we don't need that right now. Memorize, yeah. Wait, slugs, yeah, no, I know that. If we wanted to determine, a set number of... Oh, we started doing that when we didn't finish it. Yeah, xi equals x bar times n. If we want this to be over 7,500, we're trying to find the probability of something being over a limit. Then we say that the sum of them is yes, is n times... Okay, he's using the same thing, is the thing. Like, this n, he's using this interchangeably with, like, the number of... the sample? Wait, what is our n? 47. Where are we getting 47 from? Oh, all of our passengers. Okay. Yeah. That's the sum of how much stuff we're summing. Yeah, it's the size of the sample or the population. I think I can do it. I think I get it. Anyway. It's fine. Here we go. Ooh, oh, that's a question I don't know the answer to, and it's a true or false. I love that. Thank you. It's a lie. I don't like that. Okay, second one I do know. If the parent population is Gaussian, the population of the means is also Gaussian. That is true. That's a true thing. The population of means, x bar, of samples of any sign n has the same mean as its parent population. No. Wait. Okay. Brain broke. All random measurements are normally distributed? I don't think so. I think that is false. I'm gonna go ahead and say that is false, because they're random, and if they were normally distributed, I feel like this course would be a lot shorter. But that's just my gut. My 3D print finished. Okay. This is so many words. Okay. The population of means x bar of samples of any size n has the same mean as its parent population, no matter what the parent population looks like. I think that is false. I think it does, because what they're saying is like, this is the same thing, but they're saying like, okay, if you take a bunch of means, right, of a bunch of different sample sizes. So this is your this is your parent population. This is the rent. And if you take a bunch of means, you take them a million times, I don't know, a quadrillion times, like, the mean is going to end up being like the same thing, which I'm pretty sure is right. But I think it has to be Gaussian. I don't think it can be not Gaussian, because that doesn't make any sense. Population of means of samples of any size and has the same standard deviation. That one is hard. I think true, though, because I think what we were saying was, like, the reason why, if you have, like, a parent population, I'm just going to draw it, like, bigger, like, this is your parent population, and, like, let's say you get a population that kind of looks like, I don't know, something like this. It's, like, kind of Gaussian, right? Like, maybe the mean is a little bit different. Like, your standard deviation is gonna always be smaller on the smaller one, because you have less, right? Like, this is, like, the whole thing, but, like, you just have less stuff. So, like, your standard deviation is gonna be smaller. But as you take this to infinity, and you take, like, essentially a bunch of stuff, I think the standard deviation, because you're covering all the variables, which means that you're going to get that. But if it's not Gaussian, I don't think you would get the same mean. I don't know. Maybe I'm wrong. Who knows? There aren't answers for this. I might just Google it and see if I can find answers, but if he says no, I'm gonna go. I mean, if I have to go to his office hours and ask him about, hey, did I get every single one of these questions right? That's very inefficient use of both of our time, so. Okay. When predicting the mean of a population based on the mean of a sample, what happens to the confidence interval when the sample size approaches infinity? The confidence approaches... well, confidence is basically when we go to infinity, we're creating the population. So our confidence interval, like, we're gonna be... Okay. Let me think about this. The confidence interval approaches... Z approaches 1.96. This is weird. I don't think it would be that. Because this is like saying 99% or something? Wait. But like your Z should approach 0.5. What is Z at 0? It should Z should approach infinity, because you're just... Well, I don't think that's true. The confidence interval approaches infinity. Your confidence interval is actually what is the thing? Is your confidence interval the percentage, or is it the... Is it the Z value, or let's see. Let's Google that. I feel like I can... What is confidence interval? Okay, Ci equals x bar, sample mean plus or minus z times s over square root of n. Oh. Well, your square root of n is going to go to infinity. So, it's just going to be the sample mean is the thing. So it should approach a finite number. It's not going to be 0. It's not going to be infinity, because your sample mean isn't changing. I mean, your sample mean is going to become your mean. But that's so weird. Like, in this, do I have that as my confidence interval? Where is the confidence interval? We don't really calculate it like that. The way we define a confidence interval is like... I guess we kind of say that, in a way. Z is gonna go to 0, though. Wait, no, it's not. It's gonna go to infinity? Wait, fuck. Wait, did it say go to infinity? Yeah, no, okay, it didn't say go to infinity. That's so weird. I don't like that. What is this? Evaluate the integral? Why do I need to do that? I don't want to. I'm not doing that. I'm not doing that. That's not happening. Estimate the standard deviation of the normal x distribution at the right. Okay, well... Standard deviation is how far away you are from, like, the mean, I guess. It's like 1 z step, right? So if this is your... So 50 to 100... So 50 area corresponds to equals 0.5 z. Okay. I don't know. I don't know if that is right. I don't know if that's the right way to approach this. Let's not do that yet. Let me get a little snack real quick. And then I'll try that. Okay, estimate the standard. Okay, well, let's just look at what our standard deviation equals. Okay, here we go. Standard deviation equals 1 over n sigma x minus mu squared to the 1/2. Well, that would suck, is the thing. But we're saying that... Well, we know we have 100 x values. N equals 100. Oh, these are hard. Okay. Okay. X minus the mean squared. And then we take the square root of the whole thing. Because of the root sum square. Well, there are other ways we can define this. Is this the population? Yeah, that's the pop... It's not an infinite population is the thing. I don't particularly like that. So I was thinking, I was gonna say like, okay, if we know the mean, this is a population, then like this is the mean. I think I can say that this is mu. And mu equals x plus z sigma. So let's see, what if I say at x equals 0, right, mu is 50. 50 equals 0 plus 0.5 sigma. Well, see, that would be bad, because that means our standard deviation is like... No, that's okay, it's not 0.5 z. Z would have to be like big chungus over there. 0.5 is the thing corresponding to z there. Wait, let me look at our z table. Because our z tables are done from the middle. Okay, 0.5 is like 4.5. Let's just say 4.5. That is the highest number that he gives us. Yeah. Cool, so then 50 divided by 4.5 is our sigma. 11. 11.1. 1. You got an extra. I don't know, I'm gonna say 11.1 equals sigma. That's what I got from that. I don't know, I mean, maybe you could say like 90 is also 0, but like, I don't know. Like, that looks like, I don't know. They both look fine. Okay, so sketch the distribution of means of samples of size 9. How the fuck do I figure this one out? What the hell? Okay, so I know that, like, it's gonna be kind of Gaussian, but, like, not Gaussian, right? Samples of size 9. So the n matters. Let's see. Let's go to our equation sheet, of course. So we have our standard deviation of the population, so we can use that. Let's see. How do we define x? X is mu plus z sigma, but that's not x bar. Oh, okay. Okay, x bar equals mu plus z sigma over n. Perfect. So mu is 50 plus or minus I guess z sigma is well, but what is our z in this case? Over 3. Something over 3. And something times 11.1. But what is our z in this case? Do we say, like, at z equals this, at z equals this? This music makes me feel insane. This is how it is taking exams. I guess we just maybe do at like z equals 1, z equals 2, z equals... Should we just go for that? Sure. Because the number we're gonna get is our x bar. But how high does it go? It doesn't really matter how high it goes. It kind of does matter how high it goes. So like z equals 0 is gonna be, so the mean is gonna be the same. That's gonna be the highest, and then it's gonna like fall off. I guess? I don't know. Let's just say z equals 1, so 50 plus 11.1 divided by 3. 53.7. But like, where do I put it on the y-axis? What is the y-axis? Is the y-axis z value? Wait, he did one in our notes where he was like, oh, I put the... I think it's relative frequency or something? No, it's not relative frequency, I lied. Let me just look up, what's the y-axis? What's the y-axis on a Gaussian distribution? Oh, probability density. Oh, okay, probability density. Where's my probability density function? What is probability? The density equation? Oh. Oh, it's the area under. Oh, I don't, I don't like this problem. This one kind of sucks, actually. How the fuck are you supposed to do this? Wait, okay, so if I'm saying 1... Okay, this is gonna give me my height, I guess. Kind of. It's saying, like, at 53... the area is, like... a lot of the area. It's, like, higher, I guess? It's gonna fall off sooner. So like at 53, it's gonna like look like this, I think. That is the worst. That's the worst Gaussian. Okay, it's gonna like look like this or something. Equals 53.7. What was the other one? I don't know, guys. I'm trying. This is probably not right. 46.3. Something like that. Like, way skinnier. Skinnier. I think. That's hard. I don't think I'm doing that right, though. Some of it is like, I think I'm doing it right, and then it's like, he wants us to write way more, and then sometimes it's just kind of like, I don't know. My brain hurts. Okay. It's okay. We're getting there. We're getting there. We're lifting the weights. Okay. The probability density function, shown here, is complete. It spans from x equals 0 to x equals 10. Determine the value of the probability density at 0. What? How am I supposed to know? What's the slope? Well, the probability density is the area under the curve. Am I supposed to just put it in variables? Huh? There's literally no way. There's literally no way you can do this without a variable. I'm just gonna fucking say 1/2 base times height, 1/2 10 times p equals 0 equals probability density. There we go. 5p equals 0 equals p. I don't know. The area under the curve. Wait, the value of it at 0? Wait, no, I lied. That was at 10. 0. Isn't it 0? Isn't it 0? There's no area under the curve here. Unless it's just this height, which then it would just be p equals 0. I'm gonna have a stroke. What is this? I love how he just like he didn't tell us any of this stuff. I mean, I guess there are like I should probably do the homework like with solutions. That would like maybe be smarter. Let me do that. I'm switching. I've given up. Not given up. It's okay. Just normally given up. Okay, is it homework 3, you think? Or is that chapter 3, homework 3? It looks like there's less homeworks than there are weeks. These are, oh my god, these are so much easier is the issue. A non-engineer decides to strap 20 water rockets to their back and launch themselves into the air. Okay, I guess I can try that one. That one looks okay. My brain. Okay, sorry. I'm literally zoning out. Okay, here we go. Non-engineer strives to strap 20 water rockets to their back. Yippee! Violence. Okay, water rockets like these have an average of 30 initial thrust with a standard deviation. So the average is 31.275 pounds force. And plus or minus 7.55 pound force. How much initial thrust do you expect to get from a typical rocket? Use 75% confidence. Okay, so the percentage of, I don't know, shit that you do. Shit that rockets do. We have, yeah, what initial one do you expect? We're trying to predict the x, so, you know, mu minus z sigma x mu plus z sigma at 75%. So we, oh my god, okay. Okay, so we transform to z, which means that we do this, okay. P, we add mu to each of them, so minus z sigma, x plus mu. And then we have, no, I lied, we subtract mu from each of them. Whoa. Plus, over here we're gonna have a z sigma. And we want to divide by sigma, so we'll have minus z x minus mu over sigma z. Now, I'm looking at this in my notes. I'm trying to remember what he did here, because I feel like he just changed it to say z. No, I remember he didn't do it like this. Did he do it like this? Because I think you transform it then to say, like, this is equal to z. Oh, yes, 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 yes. Yes, 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 yes. So we say x minus mu over sigma, z, x plus mu over sigma. Big smart, big smart. Okay, so that's our z. So then we draw it, right? So we draw a little Gauss. And we have here. And we say this middle value is our mu. This is our x's. Trying to find an x. And then from here to here is the area we want, and that's 0.9575. So then by symmetry, sorry, say like graph analysis, area analysis. Then we say by symmetry 2 times just this part. Okay, so 75. So I'm just gonna do it in my calculator. 0.75 divided by 2. 0.375. So then A equals 0.375, Z equals, we go to our Z table, find it, 0.375 is, 0.3749 is 1.15. Okay, so then we plug in. Our x is going to be, right, so it's x equals mu plus or minus z sigma. What is our mu? Our mu is 31.275 plus or minus z, which is 1.15. Times that. $7.55. 5.755. $6.61825. Cool. Pound force. That's how much we would get. And then they want 600 pounds from 20 rockets. Okay, so 600. I'll do it on another layer, I guess. I'll do it over here. So if we want 600 from 20, obviously we want 30 at least from each of them. So 30 pounds. So 30 pounds force corresponds to what percentage? So in this one, we know mu. We know the standard deviation. We're looking for x. Oh, I mean, we're looking for the probability. X is greater than 30. So we need to, and then the percentage equals what? So out of our equations, we're just going to use the same thing here, I think. Yeah, we're looking for, we know x needs to be, it's going to be like this. Like, so p, x is greater than or equal to, 30. So the way that we do this is, well, 30 equals mu plus z sigma. So I guess we just figure out the distance. Or do I have to change it into Z? I think I might have to change it into Z. Let's see. No, I don't think I have to change it into Z. I think it's just going to directly tell me the Z value. Lol. I think it's a pretty good confidence that they would have this, is what I'm guessing. Because 31... actually, I don't know. Minus 30. So 1.275. So Z sigma equals 1.275. And then Z equals... because this divided by 5.755. 0.221. 0.221. So then we go to the chart. We look for 0.221. 0.22. Yes, okay. We're going to multiply this, so Z equals this. Z corresponds to area equals 0.0871, so then times 2 because symmetry. And I drew it out already, so like, I mean, it's whatever. It's not best practice, but 0.0871 times 2. Now this times 100 is a 17 point, so area equals 0.1742. Probability equals 17.42% chance. That's the probability of us. Okay, so probably actually not a very high probability. Although, I mean, I guess maybe it shouldn't even be that. Maybe it should be... That's like saying, is each one above 30? But maybe I should say is the sum of them... Let's see, if I do it as the sum of them, that would be a different equation. That would be the mu equals, so mu n. This is saying each individual one, what's the probability that it's over 30, which is not very high. But she cares about mu equals 1 over n sum x1. So mu n equals sum of x1. Probability. I don't remember how to turn this into a probability. How the fuck do I do this? How the fuck do I do this? Oh, I just multiply everything by n, I guess? Like, what's the probability? Okay, wait, what we're saying is this. Probability that mu n is greater than or equal to 600 pounds. Okay. So if I say mu, how do I do this? We don't know the area. I know mu. No, there has to be more. It can't just be mu n. There's like a standard deviation that you need to add in there. Huh. But I mean, mu does equal that. Oh, because I'll need to say like mu is in between x plus z sigma. Do I want to use x? I think I have to, because to say mu... This has to be greater than or equal to 600, and this equals x minus z sigma times n. I think. What is x, though? Do we know x? Do I have to plug in x too? What is x? Well, x is in between two things. Oh, wait, we found x. We found x. Wait, this is what they want us to do. This is definitely what they want us to do. Wait, but goddammit, I have to root sum square the averages. That is okay. That's okay. So x is... Okay. Okay, we're getting somewhere. We're getting somewhere. I definitely don't have enough space to do that. But it's fine. Okay, so x is 31.275 plus or minus 6.61825. That is too many decimals. Why did I even do that? 6.62. And then round this. Whatever, I don't, yeah. 7.5, you... If it's odd, you round up. I'll leave that one, but we'll leave this one. Okay, our z, do we have a z value? No, we're trying to find z. This is gonna equal 600. What's the probability that this equals 600? So minus... I guess it's plus or minus, really. Yeah, and then we say z, and then sigma is, we know sigma is 5.755. And now we have to say, okay, first off I can just get rid of the 31, right? So 600, wait, times n. Fuck, all of this times 8. Okay, so 600 minus 8 times 31.275. Okay, so we say 394. 394.8 equals... Okay, now we have to root sum square these, so 6.62 squared plus z squared times 5.755, and then this squared, or square rooted. So if we square that, then we should be chill. So this squared is a lot, minus 6.62 squared is still a lot. That is not going to get away. That's not going to get away. We're not going to get away with this. Wait. RZ is going to be tiny. That's, like, not possible. No, RZ is gonna be... Oh, maybe not, actually. We're okay still, I think. Okay, this squared is 1,22360 minus 6.62 squared equals z squared and this over 5.5 squared. Seven. I don't know, I'm writing extra numbers in there, don't look at that. Okay, no, we're okay, we're okay, we're okay. What's our z? 60. Z cannot be 60! That's like a 0% chance. Oh no, oh no. Okay, wait, I have to see how you do it. Okay, this is the last, I'm gonna, after this problem I'm wrapping up, but like, how? Z cannot be 60! It's never happening. Z equals 60. It's never happening, guys. Okay, let's see. This is the one with the solution, so I can check the solution at least. Solutions annotated, I guess. Let's see. Oh boy, okay. Oh. Okay. Graphical analysis, 7.5. Wait, oh, that's a different thing. That's a different thing. Oh shit. No, yeah, here we go, here we go, here we go. Here, let me show you guys. Okay. So, population with the, yep, with that and that, cool, we got that. Probability that it want, X, so draw in X domain, cool. Wow, okay, this is actually really good to look at these. I need to look at these before the exam. To like see what he actually wants. Okay. Draw in X domain. So I did draw it in the X domain. And then, yep, need Z, draw, yep, 0.375. Okay, cool, got that. Yes, I didn't add that, but I did get a... Oh, 2 sig figs, not 2 places. Ah. Okay. This one is crazy. Okay. The sum, yes. Okay, so I did it right the second time, which is, like, good. I mean... The other one is just a different question, I guess. So n times that is 600. We know x is Gaussian if we know x bar is Gaussian if x is Gaussian. Yes. By defining the sample mean, okay, we're getting there. I did that. So substitute p divide by 20. What? Oh, yes, I did that. Wait, why did I say 8 before? Wait, maybe it's not 60. I divided by 8. Where did I get 8 from? Wait. 600. Okay, wait a second. Okay, 600 divided by 20. This squared. Wait, guys. Wait, we might be so back. 6.62 squared. Wait, sorry, clear. 900 minus 6.62 squared. And then this divided by 5.755 squared. 25. Okay, Z is still 5, which is like a lot. So that might not be right, but like... Wait, let's see. Okay, but that's way closer. Okay, so I goofed it because I didn't get the number there. 30 minus 31. Oh, wait. Wait, I did... No, okay, I didn't do that. I didn't do that. Okay. Well, okay. Wow, okay. 84%. Damn. Okay, well, part of it was... I'll have to do the rest of it later. Anyway. I think I'm gonna wrap it now. Thanks everybody for hanging out. That was a good time. Got some statistics in here. At the very end, lots of statistics. Lots of guys. I don't know what I'm going to use for next. It might be Tuesday, might be not. Given my current schedule, I have a lot of work. But no, I think this week I'm less busy because like this midterm is on Wednesday, and then once I'm done with that, like everybody's kind of letting up on stuff. So yeah, I'll see. I do have to do statics still, so maybe I'll stream that on Tuesday if I haven't done it yet. I should do some of it today too, but anyway, thanks for hanging out, guys. I will see you all later. Goodbye.